The Haber-Bosch process is one of the most important industrial chemical reactions. It combines nitrogen and hydrogen gases in the presence of an iron-based catalyst at high temperatures and pressures to produce ammonia fertilizer that helps provide food for more than 5 billion people. For decades, researchers have sought to lower the reaction temperature of the HB process to increase ammonia yield while reducing energy consumption. To this end, they have recently developed new catalysts based on other transition metals such as ruthenium, cobalt and nickel, which exhibit much higher catalytic activity than iron. However, these catalysts preferentially adsorb hydrogen atoms to their surfaces at temperatures as low as 100-150 OC, which reduces nitrogen adsorption and thus inhibits ammonia production. This phenomenon, known as hydrogen poisoning, is an obstacle to the low-temperature HB process. In this context, researchers led by Professor Michikazu Hara from the Materials and Structures Laboratory at Tokyo Institute of Technology refocused on iron-based catalysts and modified them to produce ammonia at 100 OC. Professor Hara explains the motivation behind the research. Hydrogen poisoning is not strong for iron-based catalysts. Therefore, they can be used for low-temperature HB treatment, but only when combined with a suitable promoter that increases their catalytic activity. In this study, the researchers prepared metallic iron nanoparticles on calcium hydride particles with a mixture of barium oxide and barium hydride on them. A series of experiments revealed that the iron nanoparticles interact strongly with the hydride ions of both hydrides. As a result, hydrogen atoms move from hydrides to nanoparticles and desorption as hydrogen gas, leaving electrons behind. Hydrides donate these electrons to iron nanoparticles. It facilitates the dissociation of nitrogen gas into atoms, providing enhanced catalytic activity for ammonia production even at low temperatures. The Bar2-BaOF-ECAH2 catalyst exhibited a cycle frequency of 0.23 s(1) at 100 OC and 12.3 s(1) at 300 OC under moderate pressure of 0.9 MPa. These values, which are much higher than for catalysts based on other transition metals, are due to iron's ability to prevent poisoning by desorption of hydrogen atoms adsorbed at low temperatures as gas. Discussing the future potential of his work, Professor, the Bar2-BaOF-ECAH2 catalyst facilitates the low-temperature HB process, which consumes less energy. Therefore, it can reduce the use of fossil fuels and potentially reduce global carbon emissions. Additionally, iron is plentiful and inexpensive, which makes the HB process more sustainable. There is definitely a need for a low-temperature energy-efficient ammonia production process that is both environmentally and pocket-friendly.